Hello everyone, welcome to this lecture on the series of probability and statistics. And in the last lecture, we had discussed a problem on probability. We considered many different cases and found the probabilities of different events. Although I will keep coming up with new questions so that you get more hang of the concept. In this lecture, I would like to move further to the next topic in this series, which is conditional probability. And I would like to start by saying that till now, all the probabilities that we have calculated have been defined in a sample space, right? We started with random experiments. A random experiment has a sample space, and generally when we calculate the probabilities, the denominator, that is the probability of anything happening in the sample space, that the probability of the sample space is the denominator, and that is how the probabilities are defined. All right, so every probability we have calculated is with respect to the sample space of that random experiment. Now, sometimes it is possible that we have certain information already available with us, and we may have to update the sample space based on that new information. The thing is that in any random experiment that happens, there are certain outcomes. But suppose you have some information with you and you want to include that information in your probability calculations. So the thing is that if there is some additional information which you can include in your calculation, that may change the probability of the event. So including that information is very crucial, and probability is calculated in such cases. And in such cases, I mean that where we have certain new information which we have to include. So we calculate the probability of a certain event given something has happened or something we know that this is for sure. So if you know this thing, now calculate the probability, and that directly means that our sample space will change now, because now all the possible outcomes are no longer true. The possible outcomes will reduce. So let's take an example to understand this more better. So suppose I have a box of chocolates in which there are 10 chocolates, as you can see, out of which I have 5 dark chocolates and 5 milk chocolates. Okay, and just ignore what is written here. This is 5, as you can see, right? And this is 5. All right. And one more thing is that 5 of the chocolates have nuts. You can see the almond on top of it, and 4 of the dark chocolates have nuts, and 1 of the milk chocolate has nuts. So we can say that there are total 10 chocolates. 5 are dark, 5 are milk, and 5 have nuts. And out of those 5 which have nuts, 4 are dark chocolates and 1 is a milk chocolate. Okay. Now, suppose I ask you, what is the probability of getting a dark chocolate? All right, you just randomly pick a chocolate from the box, and the answer is very simple, right? There are 5 dark chocolates and total chocolates are 10. So this is the probability of the dark chocolate. All right. Now, suppose I've given you an information. Suppose that your friend sitting there, you tell your friend, hey, just go and pick a chocolate for me, right? And then he says that, okay, I have picked a chocolate for you, and that chocolate has nuts. In your mind, you were like, oh, I need a dark chocolate. All right, you didn't mention it to your friend. Your friend just picked up one, and he says that that particular chocolate has nuts. So now you start to think, okay, now I know that this chocolate has nuts. Then what is the probability now that I have a dark chocolate? All right. Now, what will the denominator be? Now, the denominator can not be the full 10 chocolates, right? Because if you see the chocolates I'm marking, they don't have nuts. And I know that the chocolate has a nut. So the denominator is 5. That is, our sample space has now reduced to these 5 chocolates. And out of these 5, how many are dark? 4. So now my probability of getting a dark chocolate is actually 4 by 5, which is different from what we had earlier, right? That's how the probability has changed. And this is a conditional probability. If you see over here, there's a certain way of writing. What is the probability I get a dark chocolate given the chocolate has a nut, all right? So this is the way you write it. So anywhere, now you know, anywhere you see this particular way of writing probability, it means that you're calculating a conditional probability. And I hope you understand the difference between the two probabilities we have calculated here. The only difference is the sample space getting changed, right? Until and unless your friend had not mentioned anything to you, you know that the probability is that I will either get a dark chocolate or I will get a milk chocolate. But now with the new information that the chocolate that has been chosen by your friend has nut, the denominator is 5. Okay. This is a very good way of thinking. Think it this way. Conditional probability is just the probability after narrowing our world given some information. And by our world, I mean the sample space. For any probability problem you solve, for any random experiment you're considering, your world is what you are interested in, and your world is the sample space. So this is all that I can get, right? And conditional probability means that you're narrowing your world. You have been given some certain information, you have to include that in your probability calculation. Alright, now that we have a very good intuition of what conditional probability is, let's actually look at the formal definition. Okay, suppose we have two events, A and B, and S is the sample space, and probability of B happening is greater than 0. Alright, so what is the probability of A given B? Now if we compare it to our dark chocolate example, event A is getting a dark chocolate, event B is getting a chocolate with nuts. Okay, now if I know that A and B are events in S and both are part of our sample space, that there's no doubt there, right? And we know that probability of getting a nut is greater than 0. All right, and what is the probability of A given B? How is it defined? So the answer is probability A intersection B upon probability of B. Now before we go here, right, just think of it as in the denominator it is NB. By NB I mean, so what it generally is, if the conditional probability is not into consideration, it's actually NS, right? How many elements are there in the sample space? But now the main concept is not narrowing our world, right? Now I know that B has happened, so I know that in the denominator whatever will be there, whatever the outcome is, it is one of these one of the elements in B only. So now my sample space has reduced from NS to NB. All right, and now that I know that B has happened, in the top, my probability, my number, what will I count? I will count that A and B happened together. What is the probability that A and B both have happened? All right, because I know for sure B has happened, right? And if I want to find the probability of A given B has happened, I have to see the cases where both have happened. Like in our example, right? What is this 4? 4 is actually the number of cases in which nuts are also there and dark chocolate is also there, right? That is what we are mentioning here. It is number of events in A. So this is intersection. Intersection means both A and B are happening, and in the denominator is NB. And if I divide both by sample space, by our actual sample space, right, we will actually get this formula only. And this is this is actually the most common way of calculating, of writing probability of A given B. So, but it is actually this, and hence this is the final formal definition. Okay, Now let's look at another question. Okay, suppose there is a family of four. There is a mom and a dad, and there are two children. Okay, one is elder, one is younger. Now, first, let us consider what are the different cases that are there. All right, it can either be both are boys. It can be that the younger one is a boy, the elder one is a girl. It is possible that the younger one is girl and elder one is boy, and it is also possible that both are girls. Now, suppose I tell you, ask you, what is the probability that both are girls? So I know this is my sample space. So the denominator is 4 and only one case has both girls. So the answer is 1 by 4. Now suppose I have given you some information. I know that one girl is there for sure. Okay. Now tell me the probability of both girls. Alright. So by definition, probability both girls and at least one girl by probability at least one girl. Okay. So what is the probability that there is at least one girl? So the answer is these three cases, right? So my denominator will be 3 by 4. Okay. And what is the probability that both are girls and at least one girl? So this is actually redundant. This basically means that both girls, right? Both girls and at least one girl means just probability of both girls, which is this one. So 1 by 4. And if I cancel the 4, this is 1 by 3. So now if I know that one is surely a girl, my sample space reduces to only these three cases, right? So my denominator is actually 3, and out of the 3 there is one case in which both are girls, and that is how the probability has changed. So this is also a good sentence to keep in mind. Conditional probability is really just about removing the impossible cases, but you have to be intelligent about it. You can't just take every possible information that sometimes in questions you are given you're given information which doesn't change the probability if you think about it, right? So you have to intelligently think that, okay, given a certain information, does that actually change my probability? All right. So that's what we are going to do next. So sometimes in conditional probabilities, it can be really dangerous. Information can feel useful without changing the probabilities in the way we expect. And for that, we actually have 3 to 4 problems in conditional probability, which are they are not as straightforward as you would think they are. And one problem out of these is the 3 prisoner problem, which is actually coming up in the next lecture. We will discuss it in detail so that you understand what the answer is and why that answer is. So I hope you have a clear understanding of conditional probability in this lecture, and I'll meet you next time to work on the 3 prisoner problem. I hope you enjoyed this lecture. Please let me know any feedback you have. Thank you.